we start by talking about the origin of electrical charge. What we know is charges, electrical charges exist. They are an intrinsic property of matter. We don't know why do they exist. It's just a fundamental property in nature. They exist. We know that there are two types of charge: positive charges and negative charges. What's interesting, where do these charges come from, were not really discovered till the beginning of the 20th century. Now, what people have found during the beginning of the 20th century is electrons, for example, are negative charges, and protons within the nucleus of atoms are made up of positive charges. Now, what people have learned during that time is atoms, like what we are looking at here, are made up of electrons going out in orbit around a small nucleus that's made up of protons and neutrons. The protons are positive and neutrons are neutral. That's why we call them neutrons. And they have found out actually that some atoms seem to radiate some positive charges that are the same mass as electrons but the opposite charge. And these particles are not long-lived. They don't exist in nature by themselves for long, but these particles are called positrons. A positron is a particle essentially identical to an electron. The only difference between an electron and a positron, as far as we know, is the charge. But they have the same mass. That's all what we know of them. Now, one thing that's important, an important property of charges, of electrical charge, is that they are balanced. Neutral atoms, the way atoms are normally available, are made up of equal quantities of positive charges and negative charges. So neutral atoms are made up of equal quantities of positive and negative charges. For example, neutral carbon has 6 protons and 6 electrons. And then it's made up of neutrons as well, but we're not worried about that so far. Now, when we talk of neutral atoms, it's worth mentioning that if we strip electrons off of atoms, then we end up having ions. Or if we allow atoms to capture electrons, then we also have ions. What happens is the electrons are in the outskirts of the atoms, and especially the most energetic ones in the atom. They are very much in the outside, so it is somewhat easy to strip them off, or it is also very easy to get an atom to capture other electrons. So it is somewhat a simple task to change a neutral atom into an ion. Then if it's going to capture electrons, it's a negative ion. If it's going to lose electrons, it's going to become a positive ion, since it lost the balance, it lost some of electrons, some of its electrons. Now, we can ionize electrons. We can have charges available, moving freely in nature, somewhat freely, having charges available in nature. However, whenever charges are going to flow, they are going to flow to try to maintain the neutrality. When they are neutral, when we have neutrality, that's the lowest energy state. And So positive charges will attract to negative charges to maintain that neutrality, and we have the lowest energy state that way. Now, it's worth noting that, for example, our bodies have something like 510 to the 28 positive charges and the same number of negative charges. Now, at any time of the day, that balance is not always maintained. It is maintained within trillions of positive charges. A trillion is very small compared to the number of charges we have in our body. So it's a very tiny, minute number, but it is still a large enough number for us to be not neutral. Now, the main property of charge that we know of is the fact that opposite charges attract and identical charges repel. Opposites attract and likes repel. Now, this is there is something interesting about this. Remember what we said about atoms; they are neutral. So what does that mean? In the outskirts, we have the electrons, as you see them here, going around. Now, in the inside, we have the protons. Now, this graph here of the atom is quite off-scale. What does it mean to say it is off-scale? The problem is the nucleus of an atom is about 10 to the minus 15 meters in radius. You know, it depends on how big is the atom in terms of the more protons it has, the larger it's going to get. But this is kind of an indicator of the size, 10 to the minus 15 meters. However, the size of the overall atom is 10 to the minus 10 meters. So what am I saying there? I'm saying this is 10 to the minus 10, and this is 10 to the minus 15. Now, the ratio between 10 to the minus 15 and 10 to the minus 10 is 10 to the 5. So what's 10 to the 5? 10 to the 5 is 100,000. What does that mean? So you can get a good picture of what's going on. If the size of the nucleus is about this much, what I drew here, about 1 centimeter. Actually, that's a little bit bigger than a centimeter. Then the size of the atom is going to be about a kilometer, which is about 2/3 of a mile. So imagine that. This is about the size of the width of 2 pens. A centimeter, that's less than half an inch. And this is about 2/3 of a mile. Now, in addition to that, actually these tiny electrons, their size is so tiny, it is smaller than the 10 to the minus 15. So actually they are present throughout that space, but themselves, they are so tiny, they are smaller than anything we can measure. As far as we know, as far as our precision right now, technological precision is concerned, electrons are point light. They don't occupy much space. The protons are in this 10 to the minus 15 meters range. The neutrons are at about that size as well, which means this 2/3 of a mile, that huge space, has only half an inch portion of it that's occupied with the protons and the neutrons, the rest of the space is essentially empty. It's essentially void. That's a very quite interesting thing. Another thing about charges, what we know is for particles like protons, they have exactly what we call 1 unit of positive charge. Electrons have exactly 1 unit of the negative of that charge. So a proton and an electron have exactly 1 unit of charge, except that they are opposite in sign. Now, in nature, every other charge that we see freely available in nature is going to be a multiple of this unit of positive charge, or a multiple of this unit of negative charge. That's all what we observe in nature. We cannot observe half a unit of that charge, or a third of a unit of that charge, or a tenth of a unit of that charge. All charges are multiples of that unit. And that unit is actually equal to 1.6 10 to the minus 19 coulombs. The positive one is plus 1.6 10 to the minus 19 coulombs. The negative one would be minus 1.6 10 to the minus 19 coulombs. That's one interesting thing. One of the terms we say is charge is quantized. So all charge is multiples of this tiny quantum of charge, which is 1.6 10 to the minus 19 coulomb. Coulomb is the unit that we use to measure charge. As far as we know, electrons are fundamental particles. They are not made up of other particles. So far, no matter what we did to electrons, we were not able to break them into anything else. However, protons and neutrons, it's something else. They are not fundamental particles. Now, whenever we try to break protons, like when we have protons collide against other protons, when these collisions occur, and when we break these protons, we can learn about what are they made up of. That's a lot of what's still being done in physics, in what's called particle accelerators, to try to understand the origin of matter and how matter is made up. Now, one thing that we almost know for certain right now is the protons must be made up of what we call quarks. We are not sure at this stage of if quarks are elementary or not. That's probably will take a few more decades before people will decide on that. Some people think they are. Some people think that's not the end. Quarks hold on to each other through what we call gluons. And by combining, these quarks make up protons and neutrons, and then through other combinations, they make other particles. Some particles, like the neutrons and protons, are stable particles that exist in nature long enough for us to easily observe them. However, some other particles are short-lived and we can experience them only in labs. Now, these types of particles that we get by having protons collide and protons and other particles collide, in having these collisions, people were able with certainty to agree on the composition of what we call the quarks. And I'm not going to get into that here this is should be covered in a modern physics course or in a third introductory physics course, which is not being offered here. But then the point that I wanted to mention, quarks are made up of portions of a quantum of charge. They are made up of either a half or a third, 2/3 of a unit of charge. Now, that's the only particle, they are the only particles that we know of in nature that are made up of less than one quantum of charge. However, these quarks, as far as we know so far, cannot exist in nature individually. So the only charges that we can find individually in nature are multiples of that quantum of charge.